Okay, ladies, so we're going to look at some really basic force questions, and so here's the first one, okay? We're going to look at an object. We're going to assume that that's the only force acting on the object, and we're going to figure out basically how far it travels after 5 seconds, all right? So let's take a look at this question. Okay, so it's helpful to maybe draw an object or diagram to kind of like visualize what's happening. So we have an object here that's traveling. It's going to be traveling west because that's the only force really acting on this object. Now, realistically, maybe this is something that's on the surface, and we know that there are other forces acting on those objects, but those forces they do cancel out, so we can ignore them. Okay, so like for example, if this is the weight, then this is the force of the floor on the object, which actually has to be the same as the weight, so they're going to cancel out. So the only force that we're going to consider is this, the net force of 1,000 newtons west. Okay, so that's the only force that we're going to consider in this question. Okay. Now, we have the mass of the object. So, first thing we're going to do is we're going to figure out the acceleration of the object. Right? Now, remember Newton's second law, right? And that second law is that if there's a net force, there's going to be net acceleration in the direction of that net force. So, Newton's second law says F equals ma. We could rearrange this equation to get F over m. So in this case, the net force, which is 1,000 newtons west, over the mass, which is 1,000 kilograms, would give you the answer of 1 meter per second squared. Now the unit is meters per second squared, because remember what a newton is, right? A newton is a kilogram meter per second squared. So you have a newton, which represents a kilogram meter per second squared. So you can see that the kilograms would what? Cancel out, and you're left with unit for acceleration. But that's not the question. The question is how far does it travel? But this is now where we go back to the kinematic stuff, right? Because you have acceleration and you have rest. So when we think about the distance, and we want to know what the distance is, think about what you have. You have your initial speed is 0. You have your acceleration, which is 1. You have your time, which is 5. And this is 1 meter per second squared. This is 5 seconds. What equation could you use to figure out distance traveled given initial speed of 0, acceleration of time? Yeah, so, right. And that equation, if you remember, when your initial speed is 0, ends up just simply being this equation, right? D equals half at squared. So it'll be 1/2 times 1 times 5 squared, and that will give you 12.5 meters. Okay? So, I know some of you do not like the first unit, but unfortunately the first unit is not going away because the second unit is deeply connected to the first unit. Yeah? It's going to be content too. There's always going to be math in your tests or quizzes, unfortunately. Okay, so let's look at a second question. And I'll give you time to write down the second question, then I'll go over it, okay? So the second question now is this one. So just write down and I'll explain. So, lady, it's because you got nothing better to do. No problem. So, forgot to add the amount of friction. And before I pause the video, I've added a few more things to it. Actually, after I pause the video, I added a few more things. So, we have included the mass and we included an angle. So, the difference between this question is that the force is on an angle, right? So we have to do the same thing we did with kinematics, in that we need to think about the components. So first off, we're going to consider the motion of this object. Which way do you think this object is going to move? Really? So now think about here. You're pulling a sled, right? So imagine that you're pulling a sled. So it's going to go this way, correct? So it's going to travel, the sled is going to travel along the ground, right? So here's the ground. So there's the ground. So I'm sure at some point you pull the sled. You ever think about the angle that the string is making with the ground? It's not perfectly parallel with the ground. There's an angle to it, right? But yet the sled will move in the direction along the ground. Even though the force is at an angle, we could still think about the components of the force. Here's another question. Which way would friction point? So this will be friction. So I'm going to label it FF. This, I'm going to call this the applied force, because this is what the person is applying by pulling on the string. Now, there are other forces. There's actually the weight of the sled, which is pulling down this way. And then you can clearly see here that, see this applied force? Notice that it's pointing also up. So there's probably going to be there's probably going to be the force of the floor pushing up because of Newton's third law. If the sled is exerting weight down, then we know that the floor will exert a force up. And we're going to try to actually figure out what that is in the second part of this question, okay? But first we're going to look at the first part of the question, which is what's the net force and what's the acceleration? Okay, so the sled, look, logic says probably the sled is going to move to the right. So what we're going to do is we're going to just look at the forces horizontally. Okay? Just look at the horizontal forces. And if I look at the horizontal forces, I will notice that really there is one pointing to the right and one pointing to the left. Now the one pointing to the right, we have to resolve it just like you do with kinematics. We have the amount of force. We know it's 50 newtons, because we're told it's 50 newtons. But we have an angle. So what we're going to do is we're going to resolve it by looking at what that horizontal component is. So what would you have done if this is a relative motion? Right, so it would be cosine 30 times 50, which I believe is close to 43. Can you double check? Is it exactly 43.3? Okay, so we have now the applied force horizontally. So let's think about this then. The net force, the definition of net force is sum of the forces, right? So we have one force pointing to the right, which is 43.3 newtons. And it's pointing to the right, so we're going to make that positive. Okay? And we're going to add friction, but which way is friction pointing? Left. So that would be negative. And it's 20 newtons, which I forgot initially to put in. So there is your friction. So the net force then is the sum of these two, which ends up being 23.3 newtons, positive value, which means it's to the right. So there's your net force. How do you do the net acceleration then? Yep. So it's the F net over the mass. There's a definition of acceleration is F over M. So it's going to be the net force, because that's what we're working out, over the mass. So that would be 23.3 over 10. And that's 2.33 meters per second squared, obviously in this case to the right on our diagram. Okay. So in this case, you have the two concepts, right? You have the concept of the net force, but then you have the concept of F equals ma. Yeah. Okay, so that's actually the second part of the question. So let's take a look at the second part of the question, because we're going to assume that there is no vertical acceleration. So if there's no vertical acceleration, if it's not, think of it this way: when you're pulling on a sled, right? The sled will move horizontally along the ground, but it's not going to go up, and it's not going to go down. Now, if you're going up a ramp, it's different. But if the ground is perfectly horizontal, the sled should just move horizontally. So in other words, if there's no acceleration up, and there's no acceleration down, that means the acceleration is what? 0. That means that according to Newton's second law, if A is 0, that means F is 0. In other words, the net force is 0. So it should be balanced. Right, vertically it should be balanced. So let's think about the vertical forces, okay? You have a sled. Now, you have the weight. And you can see from the diagram there is an upwards component here. And there also then probably will be an upwards component from the floor. So we have the weight, and then we have the vertical component of your applied force. And I think you know how to work that out. I mean, if this was cosine of the angle, the opposite would be sine of the angle times the force, which is 50, right? So that would be 25. So we have an upwards force of 25 newtons. The weight. So the weight is a force, and it's defined as the mass times the acceleration due to gravity. Now, F equals what? F equals ma. So your weight, if you want to know what your weight is, it's just simply this equation, F equals ma. But A is, remember, for a falling object at the surface of the Earth, it should be approximately what? 9.8. So what you will see is that instead of the letter A, you'll see the letter G, which represents just the acceleration due to gravity, which is 9.8. So what was the mass of the sled? Not 11. Times G, which is 9.8. So there's a downwards force of 98 newtons. Okay, now let's think about these two forces right now, right? You have an upwards force of 25, because when you're pulling on the string, you can see that there's an upwards component over here. There's a downwards force of 98, but those two are not balanced, are they? So we know that the sled is not accelerating up or down. So this is what we know. The F net is 0. So 0 is the sum of the forces, right? So we have a force acting up, which is 25, right here. We have another force acting up, which is the force of the, now I'm going to call it Fn. Now Fn is something that we will investigate more. It's called a normal force, and that's the force exerted by a surface. Okay? It's just a label. You know how, like, the equation is simply F equals ma, right? But then there's all these different types of forces, like there's the force of friction. There's the force in the string, which is called tension, right? There's the force of an engine. We'll call that the applied force. There's the force of gravity, right? The normal force is simply a force that a surface exerts. So I'm going to call it Fn, because normal starts with the letter N. Fnet is Fnet, right? So we have these two forces, 25 and the normal force. I'm going to label it Fn. Those are pointing up, right? And they have to add up to the same as the weight. Now, which way does the weight point? Down. So remember, we add the weight, but the weight is negative. So now what do we have? If you simplify, you have 0 equals 25 and negative 98 is negative 73 plus Fn. And then if you move the negative 73 to the other side, you get Fn equals positive 73. Which makes sense, because if normal force is 73 up, so if this is 73 up, then 73 and 25 up is 98. And 98 down, and that all cancels out. So then there's no acceleration. Okay? So again, it's the concept of F net and F equals ma. Those are the really two big ideas so far in this unit with force. F net is just the sum of all the forces, and then you have F equals ma. Okay? Where? This is the, so we know that if it's not accelerating, the force has to equal 0. In other words, the net force is 0. So that's the equation for force, right? F equals ma. The equation for force is F equals ma. Okay, it's my A. But what we did is for weights, the label for weight is Fg. So there are certain labels that you'll see. So for force, it's F, but then you'll see like little subscripts, right? And the subscript could be Fg, which would be weight. The subscript could be F net. The subscript could be little f, which is friction. The subscript could be applied force, like maybe you're pushing something. Maybe you'll see like little t for tension. It's all the same. It's still a force. It's still the same equation. It's just you should know how to label stuff so you don't get confused when you're writing an equation, right? Because if you don't know what the subscript stands for, you might not know which way the force is pointing, right? Like if I don't know what Fg is, I'm like, okay, like if I don't know that, I might think it's pointing up, and that's a big problem because the weight should be pointing towards the center of the earth. Okay, we'll do one more question. Okay, we'll do this question. Now, in this question here, we're going to set up, this is a system like maybe a few sleds stuck together. 3 in this case. And what I'll say is that maybe we have the force in this string, and let's say the force in this string is 15 newtons. Okay, so write this down, and then we'll take it up. Pause it. So in this question here, we're going to make a couple of assumptions. One, we're not told anything about friction, so we're going to assume no friction. Okay. The other thing we're going to assume is that there's no acceleration up or down. So if there's no acceleration up or down, that means the weight of this system has to equal the normal force of the surface that's pushing up. So if you want to know what the normal force is, figure out the weight. The weight is just the total mass of the system times g. So it'll be 25 times 9.8. That's the weight, and the normal force is just pointing the opposite way up. Well, Newton's third law, right? Or if the weight is pushing or pulling, you can see that the weight vector is pointing down. Newton's third law says that there has to be an opposite force pointing the other way. Okay. That would be the normal force. Yeah. So the only force that we're going to consider in this case is just the force pointing to the right. Now, this could be a train. This could be anything that's strung together or connected. So maybe this could be like 3 sleds. And what you have is you have 3 masses, and you can see that there are 3 strings, okay? But to solve this question, and you can see, by the way, that I'm going to just label, this is the first string, second string, and there's the third string, okay? Let me ask you a question. Which of the three strings should have the highest force in it, or highest tension? Shouldn't it be the first? So the first string pulls the entire system, right? The second string only pulls the last two masses. And the third string just pulls the last one, right? So what we're going to do is we're going to figure out, because we only have the force at this point. So given that string 2 only pulls on these two masses, which is a total mass of what? 15 kilograms. We're going to figure out the force at that point as simply, we have the force. We're going to figure out the acceleration at that point. We're told that string 2 has a force of 15 newtons. And string 2 pulls these two masses, which have a combined mass of 15 kilograms. So if I was to say to you, imagine that we did not have the first block, we ignored it, what would be the acceleration of these two blocks together? Right, so it would be A equals F over M, which is 15 over 15, which is 1. Now, if I'm sitting on a train and someone is in another cart, what would happen if we weren't accelerating at the same rate? Right. Either the train will separate or the carts will collide. If everything is accelerating at the same rate, then the train should be intact. So in other words, the entire system must be accelerating at 1 meter per second squared. Otherwise, it would break apart. If we can imagine like a little thought experiment, if this object is accelerating at a rate of 1 meter per second squared, and this one is accelerating at a rate of 2, then it will collide with that object, and that's not what we want. So we're going to assume that everything is accelerating at the same rate. So if I want to know what the tension in the first string is, and I know the equation is F equals ma, then all I have to ask is one simple question. Given that the acceleration of the system is the same at any point, what mass is string 1 pulling? Yeah, has to be 25. And we know the acceleration is 1, so the force has to be 25 newtons. And we know that has to be bigger than the second one because it pulls more mass. So guess what then F3 must be? It should be the mass, which is 5 times 1, because string 3 only pulls that mass at the same rate of the entire system. So it's 5 newtons. There you go. That's it. Done. Pretty neat. Okay, I'm going to stop the video now. I'll take some crazy questions.